Okay, so in this presentation I will talk about some facts that may be unexpected for some of you. In particular, we will oscillate between good and bad news. So which one do you want first? The good I'll start from the good one. The good one is that you can go very, very fast with Linux with your drives, with your storage devices. The problem is that you may have accidents. You may happen to receive, if you are a user, or to provide, if you are a service provider, a very bad service, a very poor service. And this is what I'm about to show you in two cases for the two main uses for Linux: servers and personal systems. In particular, I'm about to show you that also for I/O, it holds the popular slogan of the Pirelli tires company, power is nothing without control. This is exactly what I'm about to show you. So, for this reason, Linux does have mechanisms to control I/O. They are, how can I say, well known and widely used. Okay, I will show you what happens when you activate these mechanisms. And here is another bad news. If you use I/O control, you lose most of the speed of your drives. Linux brakes very strongly, and you go very slowly. Okay. So the bad news should be over, because now there is this component, this BFQ I/O scheduler, and it seems to solve these problems because it gives you back finally full speed and control. So full control without throwing away speed, without imposing you to go very slowly. So I'll show you this for servers, and then, as I already said, for personal systems, where in particular I will focus on responsiveness. I will provide you with details later, and I will show you that without BFQ, even with a very fast device, with a very fast drive, you have a bad responsiveness. You may have a bad responsiveness. Once again, BFQ seems to help, but let's start. So, block and queue. Linux handles drives through the block layer, a level called block layer. It comes in two flavors: the legacy block layer and the new multi-queue block layer, block and queue. There you can see a scheme. Of course, I don't want to show you all details. Processes do I/O operation, read writes. Those are translated into I/O requests, and these I/O requests are manipulated by the block layer and the components inside the block layer, and then they are dispatched to the drives to be executed. The new block layer has multiple queues, so these I/O requests are sent into multiple independent parallel queues, so that every core of your CPU can handle its own queue independently of the other cores, and they can work in parallel, so as to achieve the maximum possible parallelism, which means maximum possible speed. There are also independent queues for the device, those hardware dispatch queues, in case you have a device with multiple queues, which is the case with NVMe and the rest. But I don't want to, as I said, enter into details. The most important component for us for this presentation are the I/O schedulers, and I'll talk about them after showing you the disaster. to show you these facts, I will use, I will show you the results of some tests with this drive here. It's an SSD, SATA SSD. It's no more the fastest device, the fastest SSD that you can find on the market. It is still rather fast, 500 megabytes per second, or 70 kilo IOPS in case of random reads. Why did I choose a device that is not the fastest one? Because I wanted the storage device to be the bottleneck, because these tests are about storage, not about the fact that your storage device saturates the speed of your CPU and then your problem is on the CPU. This device was mounted on this portable workstation, this ThinkPad, and there you can see the CPU, so it's now this is it has the speed of an average CPU that you can find on a modern notebook. Even with this system that is not so fast, you can drive very fast, because Linux is very good. In particular, I ran this test here with random reads, small. Every IO request was only 4 kilobytes, the typical random read request. It was buffered IO, so IO passing through whole the stack of the IO, which means maximum possible overhead. And in particular, it was synchronous IO, which means that the processes doing I/O issued one I/O request at a time, and then waited for the completion of that request before issuing a new one. And this is the worst thing that you can do with one such device, one such drive, because these drives are fast if you keep their queues full. Otherwise, they are very slow. Even in these conditions, you still reach 50 kilo IOPS, which means that the block layer, block and queue, is rather efficient. I will use Rowan Atkinson for my examples. I don't know how popular this guy is here in Russia. Maybe someone knows him. He does these movies where he makes disasters. But in his real life, thanks to the fact that people love his movies, he became rather rich, and one of his passions is supercars. But I'm about to show you that also outside the movies something bad happened. So we have all this incredible speed. Let's use it. Let's use it for servers, let's use it for personal system. What do I mean servers? I mean serving clients of any kind, clients of video streaming, web server, databases, whatever you want. The kind of service that you prefer. Or if you want, we can use it to serve the I/O of containers, of virtual machines, any entity that may compete for storage. For brevity, I will only mention clients from now on, but imagine that I'm talking about any possible entity. This is the case for servers. As for personal systems, maybe with a very fast device, you would like your application to start very quickly, or you would like to play back your movies very smoothly. And for this, actually, I'll show you a demo that I already showed 2 years ago, just to sort of recall, but it will be just the tail of this presentation, because the main focus now is on servers. Okay, so let's do it. Here is an example. With that drive, I ran this test with 4 clients doing sequential reads, plus 1 client doing random reads. I could do that also with writes and more complex I/O. I looked for the simplest possible example with few clients, easy to, how can I say, the easiest example to show. And if you do that, you just let these clients do I/O. Of course, this is a test in which I, how can I say, emulated these clients with some processes doing reads, okay? Because I wanted to rule out any issue caused by network or other layers. This is a test for storage. You do this I/O and you get more than 500 megabytes per second. You are running at the maximum speed of the device. But how well are you driving? Okay? And I want to show it to you with the first part of a demo that I made for this conference for Linux Peter. The demo is this one. Let me readapt to the new resolution here. Okay. So, in this demo, I will also show the second part, I mean the solutions to control I/O. But for the moment, I want you to focus only on this point here. You need to control I/O. Then we will talk about the rest. And to show you that you need to control I/O, this demo shows you more in detail the result of exactly the test that I already told you. Here you don't see the name, you don't see clients, but there I use the name groups, because this demo is already focused on the solution. And the solution is that in Linux, when you want to control I/O, you use C groups. You can put groups, processes together in groups, and then you can give guarantees to every group. To every group you can guarantee I/O bandwidth, CPU bandwidth, portion of memories, whatever you want. So here imagine groups like clients. In this experiment, in this test, basically I put every client in one separate group. Okay, so there you see groups, it's clients. There is one group per client. Okay, that said, let's see what happens to the unluckiest group. Guess which one is the unluckiest group? Of course, it's the one doing the random I/O. Then I'll tell you more about this. So this is a test done with a script of the S benchmark suite. So you can do this at home if you don't have anything better to do in your home. So it started, the generators need some time to ramp up. Now you are seeing two bars, then I'll let the video go. The bar on the left shows the total number of bytes read on the device, while the bar on the right-hand side shows the number of bytes read by the unluckiest group, the one doing random I/O. The scales differ, so this scale here is much larger, so you need to read a lot of bytes to see something appear in this bar, while there, even if you read even a few megabytes, you immediately see a lot of these characters. But as you can see, you have a very high total throughput, but the unluckiest group is receiving almost nothing. If you do the math, you will see that against 400 megabytes per second, the unlucky group got just 1.4, less than 0.3% of the throughput. Nothing, it was choked. So we need to control I/O. This is what happened. And this is as real as my results. This is the real life of this actor. So let's control I/O. First, maybe you may wonder why this disaster. Well, so you don't have I/O control, but you have contention, because you have these clients that all want to use the storage. If you don't control I/O, some unlucky client process group, call it as you prefer, may have to wait for a lot of time before being served. Why? Because the I/O stack in the kernel, in the OS, and the drive may prefer the other I/O requests. A notable example is exactly the one of my test, sequential I/O against random I/O. The drive adores sequential I/O. Why? because it gets the maximum throughput with sequential I/O. So if the drive can choose, it chooses sequential I/O. About the same does the operating system. This is why Block and Queue has been equipped with I/O scheduler. At the beginning of the time when they made Block and Queue, the first thing that they did was to remove I/O scheduler. A few months later, okay, let's have I/O schedulers back, because with this I/O scheduler, Block and Queue guarantees low latency to the I/O processes, guarantees responsiveness, guarantees fairness, which is what we need in our test, guaranteeing a bandwidth to every client. There are various I/O schedulers, and more or less what they do is the same job as a traffic officer who decides who passes on crossroads when there is competition. It's more or less the same. I/O schedulers try to do what they have to do automatically, but for some goals this may not be enough. And this is the case for our test. When you have to guarantee a minimum bandwidth to every client of a service, you need something more. This something more are I/O policies. So Linux comes also with these I/O policies that are used to do I/O control. Two I/O policies are available in Linux for the moment. Now they're working to a third and a fourth one. Throttling and proportional share. The throttling policy, as the name suggests, is used basically to cap the bandwidth of processes. You limit the maximum bandwidth that a process can reach. This policy, this feature has enormous throughput problems. For these reasons, developers worked to a different feature called low limits. It's the exact opposite. Instead of saying, I limit the bandwidth of processes, you say, I want every process, every group, that would be the correct name to use, every group to have at least a certain minimum bandwidth. Low limits, at least to reach a certain low limit. The other policy is proportional share, where you assign, it's different. You don't say the bandwidth that you want to give to every process, to every group, sorry. You assign a weight to each group. And the group will receive a bandwidth proportional to its weight. Throttling works alone. It's an independent mechanism, while proportional share uses one of the I/O scheduler. It's just an interface, and it assumes that there is an I/O scheduler below that is able to actually implement the policy. And in case of Block and Queue, the implementer is BFQ. But BFQ is basically still a newcomer. Basically, no company knows much about this proportional share on top of BFQ. They don't use it. So the only solution used in Linux is throttling to control I/O. Well, and let's use it. So if this is the most used solution, let's see how good it is. I'll show you this with the second part of this presentation, but this presentation also shows BFQ, so I need to do a magic here. I don't want you to see what will happen with BFQ, so I will put a terminal. It's a very accurate and technical solution. To show you this, now in the rest of the demo, I will show you what happened with throttling and proportional share later, when both are configured so as to guarantee to that unlucky group, the one that was getting nothing, to guarantee at least 10 megabytes per second. As a comparison, I will also show you what an ideal policy can do. A policy that reaches the maximum possible total throughput while guaranteeing 10 megabytes per second to the unluckiest group. It's an ideal simulated policy. It does the best possible thing. Let me see if I can do my trick. Okay. Okay. So now, in the bottom window, here you see the simulated policy. So this is all simulated. There you see finally throttling with low limits. You will have the left-hand bar and the right-hand bar. Here the total number of bytes transferred, and there the bytes given to the unluckiest group. As you can see, throttling is succeeding. It's giving the same number of bytes. Where is the problem? There is no total throughput. It's extremely low. Okay? Let me stop here because I don't want to spoil the ending. So this is what you got. You have thrown away 80% of the speed. And with your supercar, now you have the same speed of that one, because you are going 5 times as low, like with a bicycle. Is this unsolvable? So I can finally show you what happened behind the secret window. But I think you can guess. Okay, let me skip directly to not steal your time. Okay. Now, this is BFQ. And as you can see, the unluckiest group is getting the same bytes read as in the ideal policy, but also the real total throughput is virtually equal to the ideal maximum possible throughput. This will go on. Let me see if I can skip a few seconds. So this is the final results. 100% of the speed, while 20% with throttling. All of this can be repeated. If you increase the number of groups, it's a disaster with throttling. If you add writes, it's a disaster, while with BFQ, everything is stable. If you want full details on, for example, in that LWN article. So, we made it. Yeah, I also wanted to pay homage to a great champion and a lucky man, probably. You know him? So this is all about servers. About personal system, in the few minutes, do I have still a few minutes? So, can I have the benefit of BFQ also on my personal system? Yes. But do I have to create all these groups, set weights, and all the rest? No, nothing. BFQ does everything for you. No configuration needed. You will get a very high responsiveness, low drop rate if you play back a movie, high throughput. And once again, to show this, I made several, really many demos. You have demo for everything. Hard disk, SSDs, embedded systems, Android, Debian, real phones, my phone actually, before my kid broke it. So I chose this demo here. I don't know whether I have enough time. Maybe I will try to pick just a few seconds of it. This demo is with that SSD with an older version of the kernel. It's starting LibreOffice, and this is the time that it takes if you have nothing else in the background. Let me go here. Here you can see the available schedulers. This is the old legacy block layer. So these were the schedulers. CFQ was the most accurate scheduler available in legacy block. If we start some background workload, like just reading one file, you will see that the startup time of LibreOffice Writer, 4 seconds. Okay, this is by just reading one file. Then there is a test with the other scheduler, Deadline and NOP. They do a little bit better. I don't want you to lose time on this, but still you have to wait. If you increase the workload a little bit, so at least 2 readers, because just one reader synchronous is a very small workload, then the startup time begins to grow. It becomes about 4 times as high with respect to having the device idle. You start to wait, and you can feel that there is to wait. If you go to CFQ, you can go take a coffee, because to make this work, we switch finally to a BFQ, and the startup time becomes more or less the same as if the device was idle. We can make this game much tougher with BFQ and go to 10 files being read in parallel, but still the startup time is more or less twice the startup time in case the device was idle. If we go back to deadline, again, another coffee for you. So, this was with an old kernel when BFQ was worse. I showed you this demo because I wanted to give you a feeling of what those numbers mean. Now I want to show you the current numbers. These are results like of a few weeks ago. So what do we have in this diagram? This red line here represents the time that it takes to start another large application, relatively large application and very common, GNOME terminal. If you start it without anything else in the background, without any other I/O. These bars represent the times with the various schedulers. Purple is BFQ, and as you can see now with BFQ, whether or not you have something in the background, like 10 readers in parallel, the startup time is the same. You don't even notice it. You do notice it with the other scheduler. This is a test also with writes. It increases a little bit, but more or less the result is the same. And I think that with this one, we have finished, and thank you for your attention, and then if you have questions, I'm here. Thank you.
Okay, do we have questions? Okay, I see. And sure.
Hello?
Yeah.
Is it possible to provide fair division between storage bandwidth for a single application? Like if we have some multiple threads and native IO, or just multiple threads and P read or P write?
I think that as of now, since basically threads are processes for Linux, it's already possible. If you have something that is a thread logically, but for the operating system, you don't see multiple threads, but you see only one thread, then in that case, you must put something else in the middle. But if your application is made of multiple threads seen by the kernel, then it should be already there and working.
Okay.
Hi, Paolo.
Hi.
How do you manage to be so significant faster than none? I mean, there's still device internal scheduler with a lot of buffers.
So you are asking, how did you make it?
Yeah.
Yeah, the very quick answer is 10 years of work. But yeah, I don't want to avoid your question. So, BFQ implements proportional share policy, which means everyone gets a bandwidth proportional to its weight, which means that only the active processes share the total throughput available according to their weights. So automatically, whatever is happening, everyone gets its fraction. If you sum the fraction, you get 100%. So proportional share in itself is already a very good policy to saturate the total throughput, because everyone at every time gets that portion, and if you sum the portion, it's 100%.
So
this
you sync on every portion with device?
Sync, you mean, sorry?
I mean, how you communicate with device internal scheduler. So you sync in it.
Okay, now I got you. I trick the device. Yeah, I trick the device. I'll try to tell you in a few sentences because this is something that I made 2 weeks ago. This is an improvement that entered the main line like 2 weeks ago. This is the hardest part. Let me try. If it is not clear, maybe then I can tell you offline, but let me try. Yes, for the device to be very fast, you have to fill it of requests. You are right. If you fill it of requests, you lose control. So how can you keep control and at the same time be very fast? You have to be smarter than the device. And the trick is this one. At least this is working for the moment. But I reasoned, how can I say, in the opposite direction. And I wondered, why doesn't just a single synchronous process reach the maximum possible speed? Why? Because one core is too slow. Otherwise, it was enough. Just one core, synchronous I/O, you pump request, and you are done. You don't need multiple queues, okay. So if one process is too slow, this means that if that process is alone, it is leaving some time gaps during which the device is doing nothing. So my solution is just inject some requests during those gaps. And the bet is guess the right gaps, otherwise you lose control. So it's like, I mean, you pull here and there and try to, yeah.
Okay,
I hope I conveyed more or less the idea.
Then the little elaboration. So how BFQ still suitable for really fast devices like NVMe disk or even NVD?
Yes, BFQ makes it, if you have an average CPU like that one, then you make it with a maximum speed of around 300 or 400 kiloIOPS, which means 1.6 gigabytes per second. Until that speed, BFQ makes it. Above that speed, it does not, and I'm working on a solution to go beyond that barrier because I'm trying to reach the 1 million IOPS. I'm confident, but I don't know the future because I've already made it for network scheduling. I published a paper in which we reached 20 million decisions per second. So I want, maybe I will try to port that idea to I/O scheduling because they are similar. So I'm confident that we can make it. It won't be easy, but that's the idea.
Okay, the next question.
Hi. So
Hi.
that's really good talk. Thanks.
Thank you.
Super close.
Okay. So you mentioned this has been in the development for quite a while, and the drive you used was a little bit slower than what you can probably get today because you wanted the device to be the bottleneck.
Yes.
The point I wanted to make is CFQ was good until devices started to do hundreds of megabytes a second. Have you tried this with devices that can do gigabytes a second with throughput? And also, have you observed how it affects latency of devices that are in the single digits of microseconds?
Yeah, this is what I was saying before. I've tested it up to 400 kiloIOPS, so 1.6 gigabytes per second. That's the maximum speed. Above that, BFQ doesn't make it. So yes, I have tested it, and that's the speed that I've reached. Till that speed, you have no consequences on latency. Above that speed, you start to realize that you have a problem on your CPU.
What kind of latencies would that be for the completion?
Well, you are still in the order of microseconds, the latency of your drive. But the idea is, that's the idea. 400 kiloIOPS is the speed at which BFQ is much faster than the device. So the latency of the device, of the drive, dominates the latency of BFQ. So it just adds like 10%, and you don't notice. Above 400, it starts to become 20%, 30%, and so on. So until about 300 or 400, it depends on your CPU, on a notebook, up to 300 kiloIOPS, you don't have any increase in latency.
And what do you see going forwards for devices that are much faster and single controllers that can do, say, 2
I
million
see a lot of pressure because this is the question that I'm being asked. Yes, it's nice because externally, people go on asking, okay, how will you solve this problem? Because you're becoming too slow. Internally, when I talk with Linaro guys, I said, yeah, we need to become faster. And they say, well, I don't know this problem very well. Let's see. We will. So I don't know, because first I need to better convince internal members in Linaro that it is worth spending time, because it's hard to go beyond the threshold. If you have a scheduler that does nothing, like for example none, as the name suggests, it's easy to reach 1 million of IOPS if you do nothing. But with a heavy scheduler, it's not easy. So yes, the idea is what I was saying before, but there is also a problem of convincing people to invest resources on the tons of hours that will be needed to do that. Yeah, it's not easy. You got the point. It won't be easy.
Okay, thank you. The next question.
Hi.
Hi.
And what tools you use to benchmark disk performance? And in particular, this script in your presentation, is it available?
Yes.
Thank you.
Yes, yes.
And where we can...
Yes, it's publicly available. Now I don't have the network connection. Anyway, if I close the video, if you don't find it, you can ask. Anyway, it's called the S benchmark suite, because I'm really bad with fantasy, so it was just that letter. S stands for suite, so capital S benchmark suite. But if you write S benchmark suite Paolo Valente, you should find it. And it's I made my own suite because I didn't find any other suite that did this kind of tests. It's the S benchmark suite. You should find it that way, and it is public. Last commit yesterday night, so it's being actively developed, believe me.
Thank you, and probably the last question, and please think about the best one.
Hi, Paolo.
Hi.
Long time I'm watching the BFQ. It's a great idea, I think. And I have 2 questions. One about suspend mode. When I activated BFQ and lay my laptop to the suspend mode, and after that I noticed my system was crashed.
Wow.
Yeah.
That's not good.
Yeah, I think so.
You should talk with the developer of BFQ. It's a guy, I don't know him. No. bad guy, but no. No,
well, I'll ask him.
Yeah, no. Do report this failure so that I can work on it. There is.
Not yet, but I think
it's an hypothesis.
Maybe it's my issue. I think I want to ask maybe.
You are asking me whether it happens or did it happen to you?
Yep.
Okay, so you have this issue.
I will ask. I will send you details.
Yeah. So why don't you report it?
No. I wasn't reporting that, but I thought this is my issue in my site. Maybe I should patch in kernel or.
I don't know.
Maybe you have any idea?
If you have any doubt, it's not BFQ fault.
Okay. I will send you details. Well, and the next question is. When I tried to run BFQ on kernel 4 and 90, I noticed IO throughput was really increased. Maybe it's issues in hypervisor or something.
So you saw an improvement from 4.18 to 4.19
Yep.
with BFQ. That's exactly the commit that I was talking about before. Yeah, yeah, it's that commit.
It was Giberizer, I think.
Sorry, what would you?
VMware.
Uh-huh.
VMware in virtual machine.
Uh-huh.
Maybe it's a low-level issue, or
No, it's the thing that I was telling him before, like injecting I/O while one process is without I/O requests. Yeah. Should be that one, but if it increases, it's okay.
Okay, what is the best question you receive?
Oh,
Yeah, we have press. No time.
I might say the next one, so I don't offend anybody.
We have relatively short break.
I don't know. I like all of these questions. Maybe, but actually, his question was closest to the internals of BFQ. Yeah.
Okay, so
Yeah.
you'll go to press, and thank you very much for your presentation.
Thank you. Thank you.